So I want to build upon what John and Jason have talked about with respect to aircraft observations to focus on how we can use those aircraft observations to better characterize and understand physical processes in tropical cyclones. So Gary this morning talked about the challenges in terms of intensity forecasting and how they've really lagged behind our improvements in track forecasts. So this is a graph that shows 48-hour forecast errors from the Hurricane Center over about the past 15 years. And you can see that in the case of track, our track forecast errors have reduced by 70%, whereas for intensity, the forecast errors have reduced by only about 30%, so less than half of an improvement in terms of the forecast errors between intensity and track. And that problem is even magnified when you consider cases that are undergoing rapid intensification. So if you look at over a 3-year period, 2015 to 2017, forecast guidance that focuses on cases that are not undergoing rapid intensification versus those that are undergoing rapid intensification, you can see that there's much more significant intensity forecast errors for those RI cases. And if you focus just on that 48-hour period that I showed you on the previous slide, it's actually 3 times larger. So the forecast error for RI cases at 48 hours over that 3-year sample is 3 times larger than what we saw for the non-RI cases. So why is that? Well, I think a big part of that problem, or the challenge really, has to do with the fact that intensity change, and in particularly rapid intensity change, is driven by processes that span multiple spatial and temporal scales. So just looking at a cartoon of a tropical cyclone, a mature tropical cyclone, you can see processes occur on the environment on the order of thousands of kilometers, maybe days to even a week, down to the vortex scale, maybe 100 kilometers or so, maybe hours to maybe a day or two, down even further to convective scale, maybe a few kilometers and minutes to an hour time scale, and finally coming all the way down to turbulent scale, boundary layer inflow, air-sea interaction, and those can be processes on the order of minutes, or even less. So characterizing and understanding these processes and how they interact across scales is a key component, I think, of improving our prediction of intensity change. Aircraft observations really provide a unique opportunity to sample these processes across scales. So what I want to do is I want to give you some examples of the observations that we've collected at different scales and how they've been used to improve the forecasts. So generally what we do is we have a research result, and then the information or the knowledge we've gained from that research result, I'm going to give a few examples at least of how that result has been transitioned in a sense to an operational application. So starting first at the vortex scale, this is a case of Hurricane Hermine from 2016. So I'm basically showing you flow vectors at 2 different altitudes. The blue is hard to see, but the blue streamlines are the winds at 2-kilometer altitude, and the black are the winds at 5-kilometer altitude. So at this time, Hermine was a tilted tropical depression, really. So the mid-level center here, shown by this X, is displaced about 150 kilometers to the southeast of the low-level center. The storm, again, was not intensifying. It took a few days, actually, before now you start to see the mid-level center become much more closely aligned with that low-level center. At this time, Hermine was a 55-knot tropical storm on its way to becoming a hurricane. So clearly, the relative position of the low and the mid-level centers are important in terms of driving the intensity change. So this has actually been applied or adapted in real time. So this is an example showing from Hurricane Humberto, tail Doppler radar observations that are actually transmitted in real time to the ground. The Hurricane Center specialists can look at these in real time. And so this is a plot showing you a similar thing, showing you the low-level flow in the left panel and the mid-level flow in the right panel. And again, you can see that mid-level center is a little bit displaced by about 15 to 20 kilometers. The NHC forecaster at the time, just a couple hours later, actually referred specifically to that image that I just showed you as part of their justification for their forecast. They said that the storm is failing some southwesterly shear, which is causing a strong tilt in the aircraft data. So that's a nice illustration of how that information is actually being used by the forecaster. Coming down in scale, looking at convective scale processes, this is a research study that was done about 5 or 6 years ago that looked at storms that were intensifying versus those that were not intensifying. So basically just focus on these black bars here. That's showing you the radial distribution of strong thunderstorms, convective bursts, if you will, and how they vary as a function of radius. So for the cases of intensifying storms, the peak and the distribution of these strong thunderstorms are located inside the radius of maximum winds. Whereas for steady state storms, that peak is actually located outside the radius of maximum winds. So that can be used to maybe have some at least short-term 6 to 12-hour prediction, perhaps, of the intensity evolution of a tropical cyclone based on that radial distribution of convection. So this is a case of how that information can be applied in real time. So I think John mentioned about the display system that the Hurricane Center uses, this AWIPS system. And so the nice thing about AWIPS is that you can actually incorporate information from multiple platforms, observing platforms, model output, and so forth. So in this example, this was a case of Hurricane Lane from last year. You can actually overlay the reflectivity from the tail Doppler radar. The contours are showing you the wind speeds at different thresholds from the tail Doppler radar. And then those little white crosses that you see are lightning flashes from the GLM on board, the NOAA GOES satellite. So if you actually overlay all that together, you can see where the radius of maximum winds is in this yellow circle. And you can see that most of these lightning flashes are actually located inside the radius of maximum winds. So that gives you a sense that this storm is actually probably going to be intensifying. And in fact, it did intensify from a category 3 to a category 5 over the next 12 to 18 hours. And finally, coming further down in scale to the turbulent scale, here's a research result that was derived a few years back. So what I'm showing you here are plots of radial inflow from observation. So this is a compilation of dropsons, a composite of dropsons, showing you what the inflow structure looks like for a mature tropical cyclone. You can see that the inflow is about 1 kilometer deep of a certain magnitude. And if you use a formulation of mixing in the vertical, eddy diffusivity, if you will, for an incorrect version of this, a version that overstated what the mixing was in the vertical, with the HWRF model, you can see that the inflow layer depth is much too deep, about twice as deep as what we observed, and it was much weaker. When we actually corrected the value for the eddy diffusivity based on observations, now you can see that the inflow depth is much closer to what we observed, and also the strength is much closer to what we observed. We actually tested that improved formulation in the operational HWRF model for 2 cases undergoing rapid intensification. So the black line are showing you the runs of the model using the incorrect version of this eddy diffusivity. And then the red is showing you the version using the correct formulation of that diffusivity. So you can see, first of all, that the absolute intensity error is quite a bit reduced and the bias is quite a bit reduced when you use a correct formulation for the eddy diffusivity. So those are just some examples across scales of how the research that we're doing and the understanding we're gaining is going toward transitioning to operations and improving forecasts.